Good evening, everyone, and welcome to International Observe the Moon Night here at Flandrau Science Center. But there's something special about thinking that people all over the world on this very same night are gazing up at our moon. It's our closest neighbor in the solar system, and if you haven't had a chance to look through the telescopes outside, that's a thrill. One of them even has an attachment so you can take a picture of the moon through the telescope using your phone. That's pretty cool. I did that. I'm excited about my photo. And we're very pleased and very fortunate this evening to have Dr. Pamela Gay. She is an astronomer. She's a senior scientist with the Planetary Science Institute, and she's going to give us a presentation about the moon. So please give a warm welcome to Dr. Pamela Gay.
Good evening, everyone, and welcome. Whoa. Okay, I'm just gonna hold this. Forget that. Good evening, everyone, and welcome. And I want to say there is also an audience watching us out on twitch.tv/CosmoQuest X this evening. And it is awesome to have people here in the real world and out there on the internets as well. So this evening, this is the 10th year of the International Observe the Moon Night. This is my 10th time being part of it. The first time I was part of it, I was actually in Rome, Italy. I arrived off the plane, went up to this amazing facility up on the top of a hill, and watched the moon rise over the city of colosseums and cathedrals. And it was one of those experiences where you realize it really is an object that our entire world shares. And in a lot of ways, the way our world is shaped today and the way the moon is shaped are all tied together through a terrible, violent act that happened about 4.2 billion years ago. Now, in the early days of our solar system, and here I am playing with a new piece of technology. Yeah, wow. In the early days of our solar system, it was a violent and dangerous place where the solar system had rocks flying in all directions and nothing was safe. And there was an object about the size of Mars that came flying through the solar system and hit the world that was trying to become our planet Earth. And when the two of them collided, it ended up creating this massive splash of material. All the heavy stuff from both worlds, both that Mars-sized object, which we named Theia because you can name things even if you've never seen them, from that Mars-sized object named Theia, and from that young Earth, all the heavy stuff stayed together. And it formed our planet. And all the lightweight stuff, it splashed up and orbited a few times for good measure. And then came together, and we're not entirely sure either one piece or two pieces, but eventually it all became one large whole, one large thing that is our moon. And that is not our moon, because I am apparently using a detect. I need to look. This is what happened. So this is the collision. I'm sorry, I'm using a device that is completely new to me. And so when we look up at the moon, what we're actually seeing is an object that used to be part of our world. And then it just got splashed up and became its own world orbiting us. Now, our world is not the only one that has undergone this kind of violence. And it turns out our entire solar system is shaped in one way or another through all of these different impacts. And Jupiter, that's Jupiter. This is an image from the spacecraft Juno that is able to look at Jupiter from angles that it has never been seen before. And it's funny because when you look at things from a perspective you've never seen it before, it looks entirely different. And sometimes you learn something. And in looking at Jupiter, one of the things that we've learned from orbiting spacecraft after spacecraft around it is how the material inside of it is structured, its density profile in fancy language. And for reasons that we couldn't understand for a long time, it turns out the inner parts of Jupiter, its inner core, is much bigger than we ever thought. Now, the way you get planets is you start out with a giant blob of gas and dust. You hit it with something. The shock wave of a supernova, the explosion of a star. You just compress two clouds together as they collide as they orbit around our Milky Way galaxy. Whatever it is that happens to shock that giant cloud of gas and dust, it will begin collapsing and fragmenting and spinning. And you'll end up with this big, spinning, collapsing disk of material. And in its center, you get a star. And all around it, you have this debris field. And a grain of dust will hit a grain of dust, and they'll become a bigger grain of dust. And the bigger grains of dust will hit the bigger grains of dust, and they'll grow, and they'll form basically asteroid-sized things, but we call them planetesimals because we can. And those will collide, and eventually it will build up until you get planets. Now, all of this predicts that for objects like Jupiter, you end up with this really dense core, and then it grabs all of the gas. And you end up with a hydrogen and helium atmosphere with other stuff in it, ammonia, hydrocarbons, fancy things that you have to take lots of chemistry to understand. And if you're an astronomer like me, chemistry is hydrogen, helium, and everything else is a metal. Astronomers keep it simple that way. So Jupiter, we thought it should have this dense core surrounded by an atmosphere of gases. But when we studied it, its core wasn't as dense as we thought. And people have been trying to figure out how that is, why that happens. And just a few weeks ago, a scientist working on a computer model, figuring out what would happen if you have worlds colliding, figured out that if this young Jupiter happened to have an object many times the size of Earth hit it when it was only a few million years old, it would fluff up the core. And they actually use the word fluffy to describe the core of Jupiter, and I approve of the use of the word fluffy in science. We need that more often. And so the core of Jupiter got puffed out in this collision with all this added heat and all this added force. And this tells us our solar system once had a super Earth, a massive terrestrial world. We could have had another planet, another giant rocky planet. But no, instead it had to go and hit Jupiter and give Jupiter a fluffy core. And that's science. Things building up one at a time through crazy processes that both destroy and rebuild. And this happened all over our solar system. And some of these processes created the capacity for worlds to have life. Our own planet Earth, Mars, Venus, Mercury, all these inner worlds were baked completely dry by the young sun. Our star was much, much hotter than it was a baby star. Baby stars in general, sort of like baby humans, like to throw temper tantrums and blast out, well, kids blast out many things, but they don't blast out radiation, and stars blast out radiation, so you don't want to be near a baby star. And this baby star baked all of these worlds dry. But our world isn't dry. Sometimes it seems like Tucson is dry, but the world in general, not dry. We have massive oceans. And those oceans were all delivered to our planet through a combination of impacting comets and, it turns out, impacting asteroids. Asteroids are filled with moisture, filled with ices. And all of these things bombarding our planet led to liquid on the surface of our world, and also Mars and Venus. Our early solar system had 3 worlds that all had oceans, all brought to them by impacts. And this is is one of the things that really amazes me. When we think of Venus, we think of this world, this planet that's not too different in size from Earth, that's a little closer to the sun than we are, and has an atmosphere of death. The atmosphere of Venus has clouds that move at hundreds of kilometers per hour. That's also hundreds of miles per hour. It's a lot, it's fast. You can drop balloons in and explore this world with high atmosphere balloons. And the thing you have to worry about is them just getting tumbled all over the place and stopping functioning because the winds are that violent. Now, this atmosphere is one that allows some colors of light to pass through it, and they warm the surface of the world. But just like a greenhouse, just like your car in the summer, that warm world, it's radiating up what we call infrared light. This is light so red you can't see it with your eyeballs. And that light can't get through those clouds, and it just builds up the temperature and builds up the temperature. So that Venus is hundreds of degrees. And it also rains acid. It will kill you in many different ways. If the heat doesn't get you, the acid will. If that doesn't get you, the poison gas will. It's just a world of death. But it hasn't always been. Wrong way. It's now thought that this world may have had oceans until just a few 100 million years ago. So we still don't fully understand what happened, what it is that would have destroyed those oceans. But here's the interesting thing. A new paper came out just a couple of weeks ago. So I'm talking to you tonight about new things that have me super excited as a scientist. And what this paper did was it looked at Venus, and we haven't really been able to get good images of its surface because it eats spacecraft. It's what Venus does. And we have good radar maps of it, so you can bounce some colors of light that you can't take pictures with off the surface and figure out the terrain. And it's thought that there's shorelines there, maybe. And a group of researchers went, okay, so why did Venus, once upon a time, early on in the solar system, had tiny oceans? It had basically the Great Lakes. Let's start with basically the Great Lakes. And evolved it forward. And it stayed wet until several 100 million years ago. That's cool. Now what if it had bigger oceans? What happens? And they consistently found that if Venus started with water, it would have kept water until a few 100 million years ago, when it looks like something truly catastrophic happened there. Now, we're not sure what happened. One of the thoughts is that essentially this world had massive planetary-wide volcanism all at once and released all these nasty chemicals up into the atmosphere, and it mixed with the water, and it superheated the planet and created the death world that Venus now is. It's thought that maybe there was a massive impact, or we just don't know. But something happened that changed the chemistry of the atmosphere. And it took it from this wet world to a death world. And what's cool about when it was wet is it's thought that it was somewhere from the mid-60s as the lowest temperature on the planet to 140 for the hottest temperature on the planet. So you're basically describing Phoenix. And believe it or not, you can have life in Phoenix. And so you could have had life here and on Mars. And we know we had life on our own world. And this is one of those crazy things, is what impacts bring impacts can also take away. So all these impacting comets and asteroids, they brought water to the inner worlds. They created these wet, wonderful habitats. And the majority of these impacts occurred 3 to 3.5 billion years ago, during a very dangerous time in our solar system that we call the Great Heavy Bombardment. That was not when you wanted to be here. Everything was hitting everything else. Things were moving around. It was a bad time. But since then, there's been a lot fewer impacts. We still have stuff coming in. Just last night, over the nation of Chile, they spotted fireballs falling out of the sky. Now, what that probably was a fairly large meteor of some sort that fell apart in the atmosphere. And what they were seeing was the shrapnel, the small rocks, all individually falling through the atmosphere. We're still getting hit with tons of material from space every year. Most of it hits the ocean, or most of it burns up in the atmosphere. Let me rephrase that. Most of it burns up in the atmosphere. Most of what doesn't burn up in the atmosphere lands in the oceans. In general, you're safe. You don't need to worry. But there's still some big stuff out there. And when that big stuff hits, death comes in many forms. This is a very deadly talk. Sometimes you just need to celebrate death. So when the big one came, it hit the Earth where we now have the Yucatan Peninsula, right off the coast, there in the ocean. The Yucatan Peninsula is shaped by the edge of the crater impact. And you may have seen a National Geographic article recently or it's been on a lot of the other news, they've been sending archaeologists into what they call cenotes, these deep holes along the Yucatan Peninsula that are filled with water. They're the reason that people could live out on the Yucatan Peninsula, which is a serious desert. Well, these formations are because of that asteroid strike. These places where there's water are left over by how the crater impact shaped a ring that allows water to pool. Now, when this happened, that rock falling out of the sky hit our planet so hard that the shock wave wrapped around our world. And near the impact, that shock through the atmosphere flung things with so much violence that dinosaurs and trees and soil, dirt and rocks were tossed into the air so fast they left our planet entirely. The first big life form to go to outer space was a very dead dinosaur. And I just love that image, which probably says not good things about me, but just imagine that force. And there's a lot of discussion about how the dinosaurs died. And as near as we can tell, one of the things that we don't talk about is what goes up has to come down. And as it comes down through the atmosphere, you have all these really fast-moving rocks, and they're heating up and they're giving off light, just like that meteorite strike over Chile last night. You see it in the sky. And all of those stones and rocks and dead dinosaurs falling back down, they gave off their speed as heat, and they heated up our world. The surface of our planet, all the way down to about 3 centimeters beneath the soil, like 2 inches beneath the soil, was the temperature inside an oven. Everything died from getting superheated, except for what was deeply burrowed or deep enough under the water. And so it was a 1-2 punch. You didn't get shocked to death and flung into outer space, which admittedly is a really cool way to go. You probably got baked while watching an amazing light show, which as a dinosaur you probably couldn't appreciate. And our world has continued to get struck over and over and over through the eons. This is one of my favorite craters, just in terms of prettiness. There's Barringer Crater here in Arizona, which you should go visit if you haven't. It is accessible. They have a cool little visitor center. You're not allowed down into the crater because footprints can ruin the geology, and we want to keep it safe for future generations of students to go study. So they allow students to go into it, but the rest of us just have to look at a distance, which means I, as an astronomer, I cannot go down and look either. But go visit it. This particular crater is one that's in South Africa. And you can get a sense of the scale of it by noticing all the farms along the right-hand side of this image. This is a satellite image. This is a crater basin that you cannot notice if you're just flying over it in a plane because it's so big. Our world continues to get hit over and over. And today we're trying to figure out, I did not switch slides. No one said anything. Good Lord. Okay, dinosaurs. Dinosaurs not getting hit. Dinosaurs looking up at the pretty light show that I talked all about. This is the crater. See the farms along the right? That's what can happen to our world when rocks decide to strike. Farms. You can see a few little tiny roads that are actually highways. This is something bigger than a city killer, smaller than a civilization destroyer, but still a really bad day for the entire planet. And so today, we're out there with a bunch of different spacecraft. This is an illustration of the OSIRIS-REx mission, which is headquartered right here in Tucson, Arizona. The OSIRIS-REx mission is currently out at a little tiny asteroid called Bennu. Bennu is so small you could set it down in the quad of the university, and it would just barely reach from side to side. It's about 500 meters, or half a kilometer, or 5 football fields across. It's tiny. And it's a rubble pile, which means that if it came too close to our planet, it might just kind of disrupt itself instead of hitting us en masse. This means that as it came in, we might end up with a whole lot of little rocks hitting us instead of just one big rock. And that is terrifying, because as our world turns, all those rocks would leave a band of destruction around our planet. Asteroids come in a whole lot of different shapes and forms and willingness to hold themselves together. And by studying them with spacecraft like OSIRIS-REx, there's a mission called Hayabusa 2 that is out of the asteroid Ryugu. It dropped a hat-sized rover on it Thursday night. And all of these different missions are helping us understand what is the diversity of ways that space rocks are out there, so that we can plan to someday see one and realize, oh shoot, that one's coming towards us. And we'll be able to steer it away. And the cool thing is, if we catch it early enough, one of the more effective ways to move one of these suckers is to paint it white. And this is because the sunlight bouncing off white, because white's highly reflective, just that bouncing of light is enough to move the asteroid into a new orbit, to steer it away from our world. And that should work on just about any kind of asteroid that's out there trying to kill us. You have to catch it early. You have to give it plenty of time for the light to move it. Now, other things that we're looking at is go out and put a really large chunk of matter. So basically collect all the garbage in orbit around the Earth, throw it together, put an engine on it, stick it in front of an asteroid. And all that mass will pull on the asteroid ever so small an amount and steer it away. And people talk about mounting engines on them and all sorts of other stuff. And we're going to, in the next few decades, start practicing moving asteroids to make sure that what happened to the dinosaurs never happens to us. And we also have our moon to thank. I told you that sometimes looking at things from another perspectives helps you learn something entirely new. This is the far side of the moon. This is the side of the moon that we never ever get to see from the surface of our world. And it looks totally different. When you look at the moon from our planet, you see all those dark, we call them mare, seas of lava. And this side doesn't have any of that. And some people think that the way our moon formed is in two blobs, and the smaller blob hit on this side, which is why it looks so very different. And this side of the moon is just covered in small craters from things that did not hit us. So we are very glad we have the moon, because it's able to catch some of the rocks. And we're out there constantly trying to understand more about it, because it's part of us. It's always cool to get to understand the parts that, well, aren't close enough to touch. So tonight, it's clear out. There's a moon out. Go look at it and know that there are people all around the world, today, tomorrow, this few days, sharing our sky. We're just one people, and we're the only intelligent life we know about in the universe. And we all have one thing in common, and that's that we can understand our universe. And that is one of the most amazing things that scientists, and all of you can be scientists. We can all do this together. So thank you. And I'm happy to answer questions.
We've got a question right here.
How far away is the moon from Earth?
Oh man, he asked, how far away is the moon from Earth? If you were a photon of light, it would take you a second and a bit to get there. And I don't know how long that is in miles. So a second and a bit, oh man, so it is more than 300,000 kilometers. What was it?
248,000.
248,000, thank you. I don't remember numbers, apparently. The sun is 8 light minutes away. I remember strange numbers. Okay, a different question that maybe I'll know the answer to. Thank you, you're awesome. I'm sorry I didn't know a better answer.
I'm going to jump in and let everybody know that we have these sheets called moon fact sheets, and they're out by the activities in the exhibit gallery. And so it's got a whole bunch of cool moon facts, including how far away is the moon from Earth. So after we've done with the rest of the questions, if you want to grab one of those, you'll learn a lot about the moon.
Other questions? Now, I know there's a ton of astronomers in Tucson, but on the planet, we're only 1 in a million. You have a question?
Yeah. Why is the moon ever so slightly moving away from the Earth?
So the question was, why is the moon ever so slightly moving away from us? It's actually due to the tides. There's this annoying thing in physics called conservation of angular momentum. And we've all experienced it at some point, especially when we were small children. If you stand and you start spinning with your arms out all the way, you can do it in a semi-controlled fashion. But the second you pull your arms in, all chaos breaks out. And if you do this while ice skating, you'll spin really, really fast. And this is because when your arms are out, your mass is distributed more. When your arms are in, your mass is in close, and it changes how you spin. And the amount of energy that's going into the spin and a bunch of other stuff, it gets really messy, and all of my students in the university hate doing this part of the semester. It all comes down to you have to conserve how much stuff is spinning. Now, the moon, it's pretty much stopped spinning. It's just like, hey, I'm going to look at you with the old man on the moon, and that's it. But our planet Earth is slowing down ever so little an amount every year. And in part, this is because the moon is constantly pulling on us. And we see this with the oceans rising to form the tides, and also rising when the moon is on the opposite side, because they're not getting as much gravity on them. And did you know mountains have tides? People out at Kitt Peak and Mount Lemmon and Mount Graham, when they're trying to make special observations, of objects like pulsars that are rapidly doing things. Pulsars pulsate, but it's a beam of light that's flashing past us constantly. Well, they actually have to take into consideration the change in distance created by the Earth having tides. Well, all of this motion is slowly slowing down our rotation. And as our world slows down in its rotation, conservation of angular momentum is like, okay, something else has to change. And that something else that has to change is the moon moves away slowly. So year by year, our planet is rotating slower. The moon is moving further away. And in the fullness of time, our Earth and moon would end up face to face forever. So that the same part of the Earth always saw the moon. The same part of the moon, which we already have, always sees the Earth. Now, in all likelihood, the sun is going to blow it up, do bad things, both worlds will get completely roasted, and no one will care. But it's still cool to think about this.
Regarding the fluffy core of Jupiter, how can you prove that one particular model or a simulation is actually the only way to get to that point? How do you ever know that there's not a billion other models that could give you the same result?
Yeah, the question was, how can you ever prove one model is the correct model for how you end up with a fluffy core on Jupiter, for instance? And you can't. So this is where at a certain point you have to go, what is the most reasonable model? What is the best model we have today? What is just the cool thing that I want to talk about tonight because it's interesting to me? I have to admit, I chose to talk about that paper because I think it's a really cool explanation. And it is consistent with so many other things that we see. Venus, it got hit so hard at some point, it got flipped on its head. Uranus got knocked over sideways. Our own moon got formed. It's a story that is consistent with the history of our solar system and doesn't require any special exceptions in how Jupiter was formed. Jupiter could form just like a normal, everyday giant gas giant, and then just get puffed up in a collision. Now, will we ever know with 100% certainty that that is exactly what happened? No. But it's a story that matches the evidence. And sometimes in science, that's the best you have.
You mentioned that in days of yore, there were oceans on Venus, and it must have been, quote unquote, somewhat pleasant. That it's closer to the sun. Is it not too much to believe that those oceans just got wore out by the heat of the sun and dried up into these gases that now?
So the question was, given that Venus is closer to the sun than Earth is, if it had oceans, couldn't the heat from the sun have eventually evaporated those oceans? At a certain point, the issue becomes this closed system. So if it was once a tropical world, you still have that water cycle. And while you may end up with super humidity, so it feels like a bad day in Houston, the humidity's not going anywhere. Now, humidity can drive a greenhouse effect. And it is possible that that greenhouse effect at some point ran away with itself, and it was that more than just volcanism that drove the catastrophe. Like I said, we don't fully understand what the catastrophe was. But the water is all still there. It's just mixed up in other chemicals. It's in those acids. It's like when you were in high school chemistry. I don't know if you had to do like what I had to do and mix water and other things to make new mixtures. So water can sometimes just change its form, become something new. And all that water is still there. It's just mixed in with terrible, awful acids and things that would kill us.
Any suspicion as to what the temperature might be on Venus?
We know the temperatures on Venus. I don't personally remember the temperatures on Venus. It's several hundred degrees. I'm sorry, I don't remember. I'm really bad at remembering the exact numbers.
According to the NOVA thing that just went through, it's about 862 degrees.
That sounds right, yeah.
That's the sun.
Yeah, it's death. It eats spacecraft. Yeah.
Our
Little girl all the
astronomy,
way back.
our astronomy student says about 900 degrees on Venus.
Moons around other planets, are they like similar to our moon, or are they like different? And are there any bigger than our moon?
There are, in fact, moons bigger than the planet Mercury. The moon Ganymede, which is out there orbiting around Jupiter, it is bigger than Mercury. And all the moons out there are a little bit different and a little bit the same. And this is because the same science that happens here, the same physics and geology, it happens everywhere. But each world is a slightly different composition. Each world is a slightly different mass. And so it's kind of like the difference between chocolate chip cookies and oatmeal cookies. They're both still cookies, but they don't taste the same. And so we see all of these rocky moons have craters. Some have more ice, some have less ice. The moon Titan has a thick atmosphere, and it has lakes of ethane and methane. And so we have all these different worlds, and some are similar, but none are identical. Our moon is both unique and similar scientifically to a whole bunch of other things. Science is cool that way. Yes?
Why can we see the moon here in night and only sometimes at day?
So it's all about geometry. So let's pretend that this, and I'm moving it so I don't accidentally kill myself. I want to only talk about death, not experience it. So, okay, let's pretend this wall is where the sun lives. Pretend. Now, if I'm the moon and this is planet Earth, right now, the back of my head is all lit up. Now, can anyone on Earth see, can any of you see the back of my head? So the people on Earth, if the only part of me that's bright is the back of my head, can the people on Earth see me right now? So if I'm right here, and this side of the Earth is facing the sun, this side of the Earth, it's daytime. And so they can't see me during the day. And in fact, no one can see me, because I'm all dark, which is kind of sad, but it's the way it works. Now, as I orbit, still the back of my head that's lit up, because the moon doesn't rotate. Well, I mean, that's a lie. Let me do this actually correctly, thinking clearer. So as I move, my face always stays facing the Earth. So now it's still the side of me that's facing the wall. It's illuminated. So now this half of me, this direction is dark, is light, sorry. This half of me is dark. And so half of me that's facing the Earth, only half can be seen. So this half of me is currently illuminated. And anyone who's here on the Earth, that's on this half of the Earth, can see me. And these people over here, they have daylight. So they see me during the day. These people over here, they have nighttime. They see me at night. And so when I'm right here with the sun over there, I'm half illuminated and half the world sees me at day and half sees me at night. Because the world rotates, you would all get to see me half of the day and half of the night. Now, as I continue rotating, always keeping my nose facing towards the Earth, I now have my face fully illuminated. I am on the nighttime side of the planet Earth, and people can only see me at night. So a full moon can only be seen at night. Now, as I continue going around the world, trying not to fall off the stand, I'm still keeping my face facing directly towards the Earth. And now it's this half of me, the other half of my face, that's illuminated. And now this side of the planet gets to see me for half the night and half the day. But it's the other half of the night and the other half of the day. And so every day, I, as the moon, get seen for a different part of the day. Sometimes the moon is only up at night. Sometimes the moon is only up during the day. And it changes every single day. So you should go out and try and find the moon every single day and see if you can find it. And there's going to be about 8 days a month you can't find it. But the rest of the time, it'll be out there.
Follow up on that question about the moon. So when we have a lunar eclipse, how often and why exactly does it happen? I know it's a casting of the shadow of the Earth onto the moon.
Okay, so now we're going to get even more specific. Okay, let's pretend this is the Earth, and this is the moon. Now, most of the time, okay, I'm going to have to put everything down to show you. I'm going to use my iPad to make a sun. Okay. So, I'm going to just be loud apologies. The sunlight casts a shadow like this, and the moon generally goes around and goes under or over so that there's no shadow. But the way it's going around sometimes has it so it's up here, crosses directly through the shadow, and then goes down. This going up, crossing, coming down, this is, that's because it has a tilted orbit. And when we get a lunar eclipse, it's when it crosses the Earth's equator exactly at or near full moon. And when we get a solar eclipse, it's because it crosses the equator or near the equator, depending on the exact alignment of the seasons, at new moon. And so it's just a matter of the geometry. But most of the time, the moon is above or below the shadow and just misses it entirely. Other questions? Yeah?
Is there a toxic part on Earth?
So the question was, is there a toxic place on Earth? There are many. One of the coolest toxic places on Earth is Yellowstone National Park. This is a super caldera. Underneath Yellowstone National Park is a giant area of magma. And it's slowly tilting a lake. So there's a lake that is getting tilted like a bowl getting spilled at Yellowstone. And there are hot springs, and there are geysers, and there are pools that are magnificent colors and boiling, and are filled with deadly chemicals. But it's all natural. It's all stuff that people didn't do. It's our world, and a volcano that someday will explode and do really bad things to North America, but not in our lifetime, so it's cool. Yes?
How common is the origin story of our moon? Like how many moons are just captured asteroids, how many moons have been originated by a violent splash?
So the question was, how common is the origin story of our moon? How often were moons formed through a great splash versus captured? And I can't answer that because we can only see one solar system in enough detail. And in our solar system, Mercury and Venus don't have moons. Mars has 2 captured asteroids. Jupiter appears to have worlds that it's basically a baby solar system. And there are so many different ways of explaining how its largest moons formed. And it also has moons that are clearly captured. And so, as far as Jupiter is concerned, Saturn probably has something giant shatter around it, creating those rings and some of the moons. So it's not quite a splash, it's more of a kaboom that formed. So some of Saturn's moons have a similar formation mechanism to our moon, just a different form of violence. But then you start getting into Uranus and Neptune, and their moons again appear to be captured. Well, Triton appears to be a captured object. And we're still figuring out all the rest. But we're just one of thousands of solar systems. And so in all these different solar systems, we don't know. We don't know. Get it.
What about Pluto's moon Charon?
So the question was, what about Pluto's moon Charon? Well, that's actually a really cool situation where we don't know if that was originally one object that became 2, We don't know if it's two objects that hit each other and bad things occur. We just don't know. We thought we knew. We thought we understood Pluto and Charon, and then we visited them with a spacecraft, and we realized we know nothing about them. So give us 10 years to figure out all the data. By the time you're in college, we may know the answer to that.
We have time for one more question.
You said about all of the asteroids hitting the moon, say Dustin being hit. Does that really mean there's a lot of water buried on the moon's surface and all those impacts?
Yes, there is actually a fairly significant amount of water on the moon. What's cool is through a mechanism that I'm not going to attempt to explain, water on the moon is able to migrate towards its poles. And so there is significant amounts of ice in the shadowed regions in the northern and southern latitudes of the moon. And that isn't to say that it's something that it's easy to go and scoop it up and drink it like you would with a shovel full of snow if you grew up in New England. But there is water in the minerals that you could, through very energy-intensive processes, get out. But if you've ever read the book The Moon is a Harsh Mistress, that kind of a future is potentially possible.
Thank you so much for a wonderful presentation. Let's give another big round of applause. Dr. Pamela Gay.
I will be hanging out over at the Planetary Science Institute booth for a little while after my talk. Thank you all for being here.
Thank you. And if you haven't visited the telescopes out on the mall, everybody's set up out there, and we will soon have music from the Chamber Winds Ensemble. It's a group from the U of A School of Music playing outside. Thanks for coming.
Oh,
Thank you for your good questions.
yeah, good question, too. What?
Thank you so much. Really entertaining. Good job. So much. You can hug it.
So here's another question.
Yes. Yes, that's all I know right now.
So what are you doing for astrophysics?
So we're currently mine. What did you?
I'm sorry, I didn't mean to.
Hold on. It's suddenly showing my Discord.